Hello and welcome to our Day 9 lecture for Upward Bound Advanced Math. Today we're talking about exponential and logarithmic functions. They're two different functions that are sort of related, and we'll get into how they're related a little bit later. But really just starting with exponential functions, you know, the root word there would be exponent. And we've worked with exponents in the past. Things like, I don't know, y equals x squared, right? We've got an exponent there. And we've also dealt with y equals x cubed, and so on. We've worked with a lot of those functions. Those aren't, even though they deal with exponents, they're not called exponential functions. They're actually called power functions or polynomial functions, however you want to look at that. The power function is typically just when x is being raised to a specific power. And then polynomial, you know, you've got the other stuff that is involved, say 2x squared plus x, something like that would be a polynomial function. And for all of those, the exponent is a constant, meaning it doesn't move, it doesn't change. We can look at a different one, but that involves looking at a whole new function. In this, what we're looking at today is when the variable x is actually the exponent itself. So instead of just looking at a set exponent, we're going to be changing the exponent as we go. Now, just a word of warning, a calculator would be very handy for today. I need to grab mine, it's all the way over here. It's going to prove to be pretty handy because, yeah, we'll just have to wait and see. Let's go ahead and take a look at what's going on here. So we're going to look at y equals 3 to the x. All right, so for 0, that would be like 3 to the 0, which equals 1. The first power would mean 3 to the first power, which is 3. Then we have 3 to the second power, which is 9. 3 to the third power, which is not 81. 3 to the third power. Really what we're doing is we're taking every number before it and multiplying it by 3. So maybe that's an easier way to work your way up using a calculator. And we can do that. 9 times 3 is 27. I don't know why I wrote it there. It goes right there. 27 times 3 is 81. So 4 is 81. So we see something really interesting in that we get very large numbers very quickly with exponential functions. Okay? And it makes sense because by the time I'm looking at 3 to the 6th power, 3 to the 6th power is like, I don't know, 3 squared times 3 squared times 3 squared. And those are all 9, so this is like 9 times 9 times 9, or 9 to the third power. So we can see where these numbers are going to get pretty large pretty quickly, just in that 9 times 9 is 81, and then we're going to multiply that again by 9. So we can see where these numbers would get fairly large fairly quickly. Okay. Let's look at sort of a real-world application of this, because so many times in math there are applications that we could say, hey, this actually does occur in real life, sometimes by sort of fudging some of the scenarios, but like the task for today was an exponential function. But if you're watching the video and you weren't in class, you probably don't know what that task is about. So let's take a look at this. Advancing technology. It says, let's say that a new cell phone just hit the market, and in town 10 people bought it on the first day. Okay. On the next day, each of those 10 people convinced one of their friends to buy the same phone. How many people in town now own the phone? So if one of each one of these friends said, hey, Bob, why don't you buy this new phone? It's really good. and Bob went out and bought the new phone. And that happened for every one of those 10 people that own the phone. Okay? And then, so how many people in town now own it? That one's not too difficult. That's just, those 10 people each told one of their friends to buy it, and that friend bought it. So now there's 20 people that own the phone. Okay? Then it says the following day, each person owning the new phone, so all of those 20 people go out and tell one of their friends to buy the phone. And now how many people own the phone? So we would say, 20 people own it there. And then after that, each one of those 20 people that own the phone went out and told somebody else. So then there's 40 people. The way I'm going to sort of break this down is I'm going to say at day zero is like that market day, that day that it hits the market, and we had 10 people that own the phone. After that, we had 20 people. And then each one of those 20 people told one of their friends to buy it, and they bought it. And then each one of those 40 people told one of their friends to buy it, and they bought it. So then there's 80. Then there's 160. Then there's 320. And then we got to figure out these at 10 days and at 50 days, how many people own the phone. So how can we write this into a function? And let's first graph and let's see what we can do. So at day 0, that's this line right here, there were 10 people that owned the phone. At day 1, there were 20 people. At day 2, there were 40 people. At day 3, there were 80. Day 4, there were 160. And I think that's this one right here. It's kind of hard to see. And then at day 5, there's 320, and that's right here. And that's day 5. Okay, so this graph, trying to make this a smoothish curve, helps the quicker I go, but then I can miss some points, obviously. So what we see here is we see a rapid increase, right? This is gaining speed and getting faster and faster, okay? But so how could we sort of break this down and put this into an equation? Well, we're going to use this general form right here, this general form equation where we have a times b to the x power. And so what this function takes into account is the a value, just like what we talked about before, where we had transformation of functions. That number on the outside is affecting my y values, that number being multiplied on the outside. It's affecting my y values, and it's making them escalate quicker than normal. The problem here is that we don't really know what the parent function looks like. We don't know we don't even know what the b value is to find the parent function. Because for every exponential function you need, for every different b, there's a different parent function, right? Because when we talked about parent functions, they usually just had an x in there. They didn't have more than one variable. Sorry. So let's try to figure out what we have here and how we can kind of make this work. So that a tells me the a is sort of my starting value, because if x is 0, as it was on day 0, because I want to match this up to my starting value. If the x is 0, anything raised to the 0 power is just 1. So my starting value comes from a, at x equals 0, it comes from a, just a by itself, a times 1, or a times whatever b is to the 0 power. So this precise function is going to be 10, and then the b comes from, you can look at it from a couple places. How do I get from 10 to 20? Well, I have to multiply it by 2, and with an exponent of 1 for day 1, this one right here, how do I multiply by, how do I get 2? Well, that has to be 2 to the x power. what you can think of this b value is it is affecting how fast it's changing, right? This 10, the a out in front, kind of sets my start value. And then the b value, the number that's being raised to the x power, is dealing with, well, how fast is it growing? Okay. And this one is doubling every day, so it's going to be 2 to the x power. Now that we have that, we can figure out the 10 and the 50. But you probably will want a calculator, and that may not even be enough for 50. I haven't tried it yet. So let's go ahead and look at how we're going to plug this in. I'm going to deal with the exponent part first. So I'm going to say I want 2, and then I need this xy. Notice it puts that little caret in there. And then 2 to the 10th power is 1024, and I'm multiplying that by 10. So it's going to give me 10,240. That's how many people own the phone after 10 days if this trend continues. And realize that wasn't asking too much, because I just said, hey, tell one of your friends to buy it. And a lot of companies use this marketing strategy, and they'll give you a little discount or something like that. All right, let's try the 50th. Let's see what happens here. See if I can even do it. 2 to the 50th, very large number. Multiply that even farther. And all right, let's say, let's try to pare this down a little bit. I have hundreds, thousands, million, billion, trillion. I don't even know what's after. So let's go ahead and say on the 50th day, here we go, a lot. Okay, there's a lot of people that own the phone. Now, what are some of the issues here? What could be some of the environmental, I guess, issues to this? And some of that is, I don't want to get too, I guess, political right now, but seeing as we are dealing with a pandemic right now, I would say that this really applies to the current issues that we're seeing in the real world. And so what could possibly make this stop increasing? Because just this function by itself is going to keep increasing forever. There has to be something that's going to, and maybe you've heard this term lately, flatten this out. What's that going to be? A big issue with this exponential growth model is population size. Okay, population size is probably the number one killer of an exponential growth model, because at some point everyone's going to own the phone, right? Or you're not going to have, maybe even by day 10, if you were doing it in North Bend, sorry, but we're running out of people that don't own this phone, right? Depending on what the latest census says, we may not have that many people in town to buy the phone. So that's probably the number one killer of that. And it really, and then it's just, there's other things too, as in, what if even though one of the 40 people told their friend, what if somebody else just bought it on a whim, and instead you had 81 here, and that could be another thing that sort of throws those numbers off. But yeah, there's a difference there when you turn it into something that flattens out here. That's no longer exponential. I would say the red one continues to be exponential. And I will let you look into the other one. It is called, I want to say logistic. A logistic curve. And so that would be one that would then flatten out as this blue one sort of shows that it's doing. And that's, like I said, times when you start reaching maximum population, total saturation, so to speak, when every possible person that there is to buy the phone has bought the phone, it can't keep growing that way. So that's just, a little social studies, I guess, for us. relating it to what we're going through right now. So again, that general form is y equals a times b to the x power. And keep in mind your order of operations. As we did when we were calculating, we want to figure out that b to the x power, then multiply it by a. Okay, I don't know, this problem doesn't ask what is 20 to the x power. It says 2 to the x power, multiply that by 10. Okay, and really for this, the regulations are a can be any real number. I'm going to say not equal to 0. If a was 0, then this would be really boring, right? Because 0 times anything is 0. It could even be 1. I know that we had 10 here, but it could be 1. In fact, I would really say I would relate, I guess, the daily task to a being 1 in that case. That penny on the first day, 2 pennies on the second, and so on and so forth. And then b is any positive number. Any positive real number. And those are the only restrictions that we have, those two things. Okay? So what we looked at here is we had b at 2. Well, what happens if b is a fraction? Let's fill out this table of values. Notice here I have a at 0, but b is a fraction. It's 1/3. So let's try to figure out what happens there. Let's start with let's start at 0, work positive, then work back to negative. 1/3 to the 0 power is always going to be 1. Okay. 1/3 to the first power. Anything to the first power is just the number that you wrote, so that's 1/3. And then 1/3 to the second power is 1 to the second power over 3 to the second power. You kind of distribute those powers if you remember your rules of exponents. 1 squared is 1, 3 squared is 9, so this is 1/9. So on the positive direction here, at 0 it's 1. At 1, it's 1/3, maybe right there. And at 2, it's 1/9, and that's even hard to graph. And then at 3, it would be probably even smaller. Let's look at our negative powers here. Let's see, 1/3 to the -1. What does raising something to a negative power do? It actually flips it over. So this would be like 3/1 to the first power, which 3/1 is 3. 3 to the first power is 3. So at -1, it's 1, 2, 3, I guess right there. And then to the -2, 1/3 to the -2. Again, the negative will flip this, making it 3/1. And 3/1 is 3, squared is 9. So there it's 9. I think this graph goes to 10. 3, 4, 5, 6, 7, 8, 9. Yep, it does. So that gives me a point right there. And then trying to make this a smooth curve. So the question is, that was a terrible ending. The question is, will this graph ever hit 0 as a y value? Okay, will it ever cross this x-axis? Can this function live down here? Well, let's think about that really quick. And what would that require? Obviously, if it's going to happen, it's going to happen way over this direction, right? With a really big x value. Well, let's think about that. Let's think about like x being 100. If x was 100, then I would have 1/3 to the 100th power, which really means 1 to the 100 over 3 to the 100. In order for this fraction to be less than 0, something here has to be negative, and are either one of these going to give a negative answer? They're not. 3 to the 100 is just a really big number, 1 to the 100 is 1. So I have 1 over a lot. So that's a really small fraction. So no matter what, this is never going to touch 0. It's definitely not going to cross 0. It's going to approach 0, and that sort of gives us that idea of limits. Okay, as x gets really big, this graph gets really close to 0. Okay. So this first one, with with the b value being a whole number, or a number bigger than 1, this one shows exponential growth. And the one down below with with b being a fraction, it shows what we call exponential. It's not growing as we move to the right. We call it exponential decay because it's getting smaller, and things like this are like half-life problems, and you'll see a lot of those because people grasp at straws for real-world applications of exponential decay. Okay. All right, so let's take a look at working backwards a little bit here, and this is more from an algebra sense than a graphing sense. But let's say I knew that 8 was 2 to some power, or I wondered if it was. Is there a way that I can find out what that power would be? Or in other words, I want to try to solve this equation. 2 to some power is 8, and maybe you know it, maybe you just know it off the top of your head. That's great, but I challenge you to think that I could probably give you a problem that you don't know what that x would be. You might guess it, you might get lucky, and that's fine, but let's see if we can find a way to do that. And there actually is, and it involves logarithms. So what we call logarithms are sort of the opposite of raising to some unknown power. And really what it comes from is these two forms that actually have everything that we're looking for. So we want to know the answer, 2 to what power is 8? The way we would find that is finding the log with a base 2 of 8 equals that power. Okay, and in this situation, the power is 3. That's a great way to show that that's in the exponent. The power is 3. 2 to the third power is 8. And if I found the solution to log base 2 of 8, it would tell me that it's 3. So these two things work hand in hand. So the way we think about this is sort of I always think of the terminology of each one of these things. In this, I have base, exponent, and product, for lack of a better word. It's sort of a product, just an expanded product. So base, exponent, product, when I look at the logarithmic form, or if I look at this in logarithms, log of my base of the product equals the exponent. So it's a way for me to find out what this missing exponent would be. The only problem is, as I look at a calculator, I have two things that deal with logarithms, and one very basic one says log, but okay, that didn't work too well. Yeah, this is one that requires it backwards. But there's a log here, and then this one down below it is ln. It kind of looks like in, but it's ln for natural log, or log of natural base is why it's ln. And neither of those let me do any log that I want to do. Using this button right here, I can raise any power to any power. I can say 5 to the 12th power, even though the only ones I had here, I have x squared, and if I go to second, I can use x cubed, but that's it, right? But nothing on the calculator other than this x to the y power lets me raise anything to any power that I want to do, which is great. And this is the way most calculators work. So we need a tool to be able to calculate any log that we want to calculate. We're going to do that with what's called the change of base formula. And it says that if I want to find the log of any base b of any product a, all I have to do is, I wrote 10 here, but this is the same as the log that's on your calculator. But if I take the log with a base 10 of a over the log of base 10 of b, that's going to tell me the same thing. That's going to give me the same result, okay? And that's what I said this is useful, because the log on your calculator is log of base 10. It's what we call the common log, all right? Let's check that with this problem here. I want to do this problem using my calculator. And I close my calculator, so that's handy. So I want to try log of 8 divided by log of 2. And on this calculator, again, I have to do things backwards. Sometimes you'll have a calculator that has you put in log, and it'll show you, okay, you want to find log of what, right? They'll open up a set of parentheses, and then you type in a number. You'd type in 8, close those parentheses, and then say log of 2. I have to do that a little bit backwards. I have to put in 8, then hit log, and then I'm going to divide that by 2, then hit log again. And then I have to hit equal. So this doesn't tell me what I want it to, because it's telling me actually the log of 2 right now. When I hit equals, that's going to tell me log 8 over log 2 is 3. Okay? So let's see that in action a couple times here and find out some logarithms. Okay? So I want to find log base 2 of 2. The way I'm going to do that is log 2 over log 2. Well, what do you think I'm going to get? I should get 1. Let's see if it works out. 2 log divided by 2 log equals 1. Okay? That may have been surprising from here, but once I wrote it in the change of base formula, it wasn't too bad. Let's go back and figure out what that means in this version up here. Again, the equals is my exponent, right, in this conversation here. This is my base, so this is really saying 2 to what power equals 2. Okay? Similarly, for this problem, this is saying 5 to what power equals 1. That's what this one's saying. Maybe you know what that is. But what I'm going to do on the calculator is say log of 1 over log of 5. So 1 log divided by 5 log is 0. And that's what it would take as an exponent. It would take 0, 5 to the 0 power, to give me 1. Here's more of an interesting problem, still using the 5. This one is saying 5 to what power equals 125. Maybe you know it. Let's check it with change of base formula. So I'm going to do 125, log that, divided by 5, log that. Hey, look, 3. And it does work out that 5 to the 3rd power is 125. I tried to stick with whole number answers here as best as we could. And I do like seeing what it kind of means in the exponential world. This one is saying 4 to what power is 64. And again, maybe you can guess that. If so, cool. But I'm going to do log of 64 divided by log of 4. And it again is the third power, or the answer is 3. Log of 0.2 over log of 5. is -1. Let's see if that makes sense. This one was asking 5 to what power is 0.2? Well, another way to write 0.2 is 1/5. And yeah, that makes sense. If that was a -1, that would be, that would do that flip thing. It would flip it over. Now here's a weird one. I have, and once I write this, it's going to make a lot more sense. Let's figure out what 3 to the 8th is really quick. This is really saying, what is the log base 3 of 3 to the, let me write that, log base 3, what was that, 6,561. Right, that's an ugly one. Let's see if I can figure this out without using a calculator and making life a little bit easy. Then I'll check it with the calculator as well. So what does this mean again? This means 3 to what power equals this thing? Well, that looks like it got a lot easier. I wonder what it could be. 3 to what power equals 3 to the 8th power? Well, x should probably be 8, I think. Let's check that using a calculator. So let me log that and divide that by the log of 3. And I get 8. So we're good to go. Okay? But just know that sometimes if you're going to go through all that work to use a calculator, it might be easier to write it in a similar form and see if, that made that a really easy answer. I would rather do that. All right, let's look at graphing logarithms really quick. I'm not too sure why this table got really large like this, but that's okay. I'm going to stick with positive values because that's what my graph has. Let's try 0, 1, 2, 3, and 4. Maybe that's a bad idea. I don't know. I'm not that picky. Actually, I don't know if 0 is going to work. Yeah, 0 does not work as an input, so instead I'm going to use 1 through 5. And we'll see why 0 doesn't work once we get to graphing it. So let's use 1 through 5, 3, 4, and 5. So let's go, so that means I'm going, that means I'm going log base 2 of x, so of 1. So I'm going to go 1 log divided by 2 log, should give me 0. Let's see, 1, nope, I don't want that again. I want 2 log divided by 2 log, well that's going to give me 1. Let's go 3 log divided by 2 log. And it makes sense to get some ugly answers, so we get 1.58. Because that's saying, that's got log 2 of 3. So that's saying, and let me put that down where it should go. And what that's really saying is 2 to what power equals 3, right? And that's not an easy answer. Oop, tried to erase. The next one should be okay. We'll see. 4 log divided by 2 log is 2, which makes sense because that's saying 2 to what power equals 4. And this one's probably going to be an ugly answer again, but that's okay. We can get a feeling for what it does. 5 log divided by 2 log, 2.32. All right, so at 1 this is 0, at 2 it's 1. Yeah, I guess that's 1. At 3 it's 1.5. At 4 it's 2. and at 5 it's 2.32. So it's starting to taper off and sort of flatten out. Because 0 is an invalid input, that really only leads me to believe that if I plugged in some decimals, I get some very big negative numbers. So it looks something like this. Okay, and it takes a while to get to 3, where this would equal 3 is at 8. I think I have 8 on here. 6, 7, 8. So it should be at 3 right there, because 2 to the third power is 8. Okay, so this one starts really low, and the closer and closer I get to 0, the bigger negative number I get here. So we need a new parent function when we want to look at the log base 3. So we'll do that again. And maybe I pick some better numbers. We can use 1. Let me use the same ones, I guess. We'll see how they're different. Otherwise, I would try to pick some better numbers. So 1 is going to be 0 again, because how do I get 1 right here? 3 to what power gives me 1? It has to be 0. 2 to what power gives me 3? I think we already did that, but we'll check it. Sorry, 3 to what power gives me 2? So now we haven't done it. So 2 log divided by 3 log, 0.63. 3 to what power gives me 3? That's going to be a 1. Sorry for going quickly through this, but you can check all these. 1.26 and 5. 1.46. And in fact, it would take all the way to 9 to get 2. So I'm going to mark that one on here as well. So at 9, this one's 2. At 3, 1, 2, 3, this one was 1. And then we had a couple points in between there. And at 1, it was 0. All these are going to have, all logarithmic functions that haven't been moved are going to have this 0.10. Okay? And then you're always going to have the point, whatever your base is, so this one was 3, that's always going to be at y value 1. Just like this one was at 2, 1, because its base was 2. And they're all going to start very low and then flatten out up here. Okay? So hopefully that helps make sense of exponential and logarithmic functions a little bit. And again, our videos just seem to get longer, but that's because our content is starting to escalate a little bit. Okay? Hopefully that helps. I hope to see you next time, and have a good day.